Standard deviation is a concept we introduced in 2.2, where we found the variances and standard deviation of various distributions. What we're going to do in 2.3 is talk about some of the different ways standard deviation can be used. Specifically, we're going to look at two things, the first of which is the empirical rule. The empirical rule is specific to bell-shaped, mound-shaped, normal distributions. So all three of those words are keywords that let me know that I might be using the empirical rule when I see them in problems. So specifically, again, if it says it's a mound-shaped distribution, it's a bell-shaped distribution or a bell curve, or if it's a normal distribution. That distribution is the most studied distribution in statistics. Really, it's going to be the focus of the third and fourth units in this class. So it's something where we know a lot about what lies underneath the distribution, so much that we can give pretty exact percentages of what lies X standard deviations away from the mean. Specifically, within one standard deviation of the mean, 68% of the data is within one standard deviation. So when I say 68% of the data, if you spread out all the data points, when you have a normal distribution, the highest numbers are in the middle. You're most likely to be closer to the middle. Then as you get further and further away from the mean, you have smaller and smaller probabilities. So for instance, a normal distribution would be like the heights of men in American society. So you would have some mean, let's say like 5'10", 5'11", I don't know what the mean would be, where that's the most likely, and then it becomes less and less likely as you get further away from that mean. So let's say that the mean is 5 foot 10 inches and the standard deviation is 3 inches. According to these numbers, if it followed a normal distribution, which it does, 68% of all American men would be between 5'7" and 6'1". If we went out further to 2 standard deviations, we would say that 95% of American men are between 5'4" and 6'4". We could go even further and say 99.7% of American men are between 5'1" inches and 6'7" inches. So all those numbers are made up. I don't know what the actual mean and standard deviation are, but it would be something close to that. And the general idea is because things are much more bunched up around the mean, if you go one standard deviation in either direction, you have a lot of the data points there. If you go 2 standard deviations, you get up to 95%. Again, 19 out of 20 possible people would fit into that. And then you get to 99.7 when you go 3 standard deviations out. These are 3 key numbers that are going to appear in a chart that you definitely want to put in your notes that you can then use to solve the problems that are coming. So what you want to take from this slide is that when you have a normal or bell-shaped distribution, plus or minus 1 standard deviation is 68%, plus or minus 2 is 95, and plus or minus 3 is 99.7. Later on in the presentation, there's going to be a nice, concise table that summarizes this information as well as more information that's coming. That's really the reference that you're going to use in the future. So, here's the way a question could be asked. Suppose that snowfall in Jenkintown for the month of January has a mean of 4 inches and a standard deviation of 1 inch. Assuming this is an approximately bell-shaped distribution, what percent of January snowfalls are between 3 and 5 inches? So, the way that I would solve this is I would start by picking out 4 key numbers in the problem. The first number I need is the mean, then the standard deviation, and then 2 between numbers. So I pick out that the mean is 4, the standard deviation is 1, and the between numbers are 3 and 5. What we really want to find out is how far, in terms of standard deviations, did we move from the mean to get to the between numbers. So we're going to take each of the between numbers and subtract the mean. Specifically, 3 minus 4 and 5 minus 4. 3 minus 4 is negative 1, 5 minus 4 is positive 1. So we know we've moved a raw distance of negative 1 to positive 1 from the mean. But we want to put that in terms of standard deviation. In this case, since the standard deviation is 1, if we take that 1 that we moved in either direction and divide it by 1, we still get 1. So basically, this is 1 standard deviation to the left, 1 standard deviation to the right. We know from the previous slide that when something's plus or minus 1 standard deviation, 68% of the data points fall within that range. So if I was answering this question as what percent, my answer would be 68%. In Cengage, I believe they ask it as a proportion, so you just want to report the answer as a decimal. Here the answer would be 0.68. Second one says, suppose that the number of books a student reads while pursuing a college degree has a mean of 12 with a standard deviation of 3. Assuming this is an approximately bell-shaped distribution, what percent of college students read between 6 and 18 books while getting their degree? So, same steps here. We're going to start by taking the between numbers and subtracting the mean. The between numbers are 6 and 18. The mean is 12. If I do 6 minus 12, I get negative 6. If I do 18 minus 12, I get positive 6. Again, this negative 6, positive 6 should be seen as the raw distance you've moved from the mean. We want to put it in terms of how many standard deviations did you move. So if I move 6 in each direction and the standard deviation is 3, I take 6 divided by 3 and I get that I moved 2 standard deviations away from the mean. Since I know now that I moved plus or minus 2 standard deviations, and I see in the prompt that it says bell-shaped distribution, just like it said bell-shaped distribution before, that keyword tells me that yes, I can use the empirical rule. So I can say, since it's plus or minus 2 standard deviations, under the empirical rule, 95% of the observations should fall between plus or minus 2 standard deviations. So 95% of college students should read between 6 and 18 books while getting their degree, if it really was true that the mean number of books was 12 with a standard deviation of 3. As always, I really just make up the numbers for these examples, so I think that they're pretty good guesses, but this isn't something that was gathered and data tested. So this is showing step by step what I just did. Basically, I start the between number minus the mean, between number minus the mean. Once I get this raw distance, I divide by the standard deviation. It tells me I'm plus or minus 1 standard deviation, which by the empirical rule is 68% of the data. For the second one, I start at the between numbers. The between minus the mean gets me to the raw distance. I take the raw distance and divide it by 1 standard deviation. This tells me how many standard deviations I moved in either direction. Since I know I'm plus or minus 2 standard deviations, and I know it's a bell-shaped distribution, 95% of the data would fall between these two values. Next thing we're going to look at is similar. I know this is a lot of words up here, so again, I'm going to point out what I really care about on this slide, but basically, when we do the empirical rule, we know something's mound-shaped, bell-shaped, the thing is most studied in all of statistics. So we know a lot of information about it. It's really the most we can know about a distribution, as opposed to Tchebysheff. Tchebysheff gives us a chance when we know absolutely nothing. So you can kind of see it as empirical rule tells us best case scenario, we include this percent. Tchebysheff kind of tells us the worst case scenario. If we don't know anything else, we know for sure this percent of the data lies between this many standard deviations. So what Tchebysheff tells us is for 1 standard deviation, we really don't have any info. I would put it in as 0 in the system. I'm not sure what percent of the data lies between plus or minus 1 standard deviation. But when we get to plus or minus 2, we know at the very least 75% of the data must lie plus or minus 2 standard deviations. When we get to 3 standard deviations away, we know that at least 89% of the data, at a minimum, lies between plus or minus 3 standard deviations from the mean. So, what I do at the bottom is tell you where I got these numbers, because honestly, when I had to memorize them, they helped me when I could go back and use this formula. But you absolutely will never need to use this formula if you just have these written down, since really all the tests in this class are open notes when we're doing them online. You don't need to memorize it. That said, if you're interested in where it came from, Tchebysheff used this formula that said 1 minus 1 over k squared, where k is the number of standard deviations. So if I put in 1 here, I get 1 minus 1 over 1, which would just give me 0. That's why he gets no info for 1 standard deviation. If I put 2 into here, 1 over 2 squared would give me 1 over 4. 1 minus 1 over 4 is 3/4. So that 75% comes from doing 1 minus 1 over 2 squared. Finally, The last entry for 3 standard deviations comes from doing 1 minus 1 over 3 squared. 1 over 3 squared is 1/9. 9/9 minus 1/9 is 8/9. So 8/9 is where the 89% comes from. Again, really what you need to know is just what the values are for each of the 3 possibilities. No info if we have plus or minus 1 standard deviation in an unknown distribution, 75% if we have plus or minus 2 standard deviations, and 89% if we have plus or minus 3 standard deviations. This looks very similar to what we just did with empirical rule. The key difference is it tells us it's an unknown distribution instead of being a mound-shaped, bell-shaped, or normal distribution. So here it still gives us that the mean number of nurses in an emergency room is 7, the standard deviation is 2. If the data follows an unknown distribution, what's the minimum percent of the data that falls between 1 and 13 nurses on duty? Same steps, we take our between numbers, subtract the mean. 1 minus 7 is -6, 13 minus 7 is +6. Once I figure out the raw distance we've moved, I need to put it in terms of standard deviation. So we moved plus or minus 6. When I divide that by a standard deviation of 2, I get plus or minus 3 standard deviations that we moved away from the mean. If we moved plus or minus 3 standard deviations according to Tchebysheff, that means a minimum of 89% of the data must fall between those 2 numbers. Again, this is showing step by step what I just said out loud. So we take the between numbers 1 and 13, we subtract the mean of 7, that gets us to the raw distance that we've moved away from the mean. When I then divide that raw distance by the standard deviation of 2, I get how many standard deviations I moved left or right. All of those steps are the same whether it's empirical rule or Tchebysheff. The last step is I look back to the prompt and see whether it said unknown or mound-shaped. Based on that choice, I then decide whether I'm going to use the percentages from the empirical rule or the percentages from Tchebysheff. In the end, this is really the chart that you need to know. This is the way WebAssign wants you to put in your answers, is as these decimal answers. So if it's plus or minus 1 standard deviation and it's from a normal or mound-shaped distribution, I'm in this column, this row, and I'd answer 0.68. If it was 2 standard deviations, 0.95, 3 standard deviations, 0.997. If instead it was an unknown distribution, 1 standard deviation, no info, 2 standard deviations, 0.75, 3 standard deviations, 0.89. Another way you might be asked these in WebAssign is to create your own intervals. So if you're told the average hours of sleep per night for a college student were recorded and found to have a sample mean and variance of 7 and 1.21 respectively, calculate x bar plus x, x bar minus x, x bar plus 2s. All these are real easy where I'm just plugging in x bar and s and letting my calculator do the rest. It's a little tricky the way that they worded it though. They've told you that the variance is 7. A variance of 7 is s squared. A variance of 7 and 1.21. Mean of 7 and variance of 1.21. A variance of 1.21 is really s squared. To get back to s, or the standard deviation, I need to take the square root of the variance. So before I can find these intervals, I need to take this 1.21 and put it under a square root of my calculator. If I do that properly, it should tell me that the square root of 1.21 is 1.1. So when I'm making these intervals, this is going to be 7 plus 1.1, which gives me 8.1, 7 minus 1.1, which gives me 5.9, 7 plus 2 times 1.1, which gives me 9.2. This really should be x bar minus 2s, I'm sorry about that typo, but I would continue in this way where I'm just plugging in for x bar 7, plugging in wherever I see an s, 1.1. Just remember that they tell you the variance s squared, you need to take the square root before you start making the intervals. When it asks me what fractions of the measurements I'd expect to fall into these intervals, really I can just put in what my decimals are. I don't have to, it has nothing to do with the intervals that I formed here. This is really just asking me to repeat back the empirical rule. So plus or minus 1 standard deviation is 0.68, plus or minus 2 standard deviations is 0.95, plus or minus 3 standard deviations is 0.997. This is showing all of those things. I'm sorry that it's kind of off to the side there, apologies. But basically, I take x bar minus s, as long as I did this variance s squared equals 1.21 and took its square root. I'm adding together 7 plus 1.1 to get this 8.1, minus s 5.9, 2s gives me 9.2, minus 2s 4.8, plus 3s 10.3, minus 3s 3.7. Again, all that I'm plugging in is 7 where I see an x bar, and then multiplying by 1.1 and either adding and subtracting. Again, for these three answers for the empirical rule, I'm just repeating back what those probabilities are: 0.68, 0.95, and 0.997.